So welcome to the lesson on the three-dimensional Cartesian plane. As you can already see here, this is a direct follow-on to the lesson on the normal Cartesian plane. So if you haven't seen that video, you should watch that first. Or maybe you already know about the Cartesian plane, in which case you can keep watching. But just to refresh you very quickly, the Cartesian plane can be formed by taking the Cartesian product of the real numbers with themselves to make this set which we call r squared. We explained that r squared is going to contain every possible pair of real numbers, where the first number represents the x point and the second number represents the y points. We also explained that there were two very popular ways that you could visualize r squared, which is this way and this way over here. In the first visualization, we let the first real number set belong to the first number line, and the second real number set belong to the second number line. After this, we explained that if you chose an x-coordinate and a y-coordinate and just joined them with a string, this would be a nice visualization for this coordinate xy. However, we explained that the major drawback with this method is that if you draw more than one string at the same time, things can tend to become really convoluted, and it's very hard to make out what you're looking at. This is a problem that is largely fixed with this visualization. In this visualization, every single point maps to a separate place on the 2D plane. After choosing a particular point on the xy plane, if you shine a light downwards, the place where the shadow is cast is going to be the x-coordinate. If you then shine a shadow to the left, the place where the shadow is cast on the y-axis is going to be the y-coordinate. This has the benefit of making it very easy to see what shape you actually have if you have more than one coordinate. As you can see, this looks like a five-sided shape. But as you transition to higher levels of mathematics, this method over here actually has one really big fatal flaw that I'd like to talk about on a new page. Now I want you to imagine that instead of just visualizing r squared, which are just coordinates that have two numbers in them, we're going to try visualizing r cubed for a moment, which are going to be coordinates that have three numbers in them, and therefore they're going to need three number lines. So if you're imagining coordinates that have three numbers in them, generalizing the method from the last page is really easy. You just have to draw a third number line, and then you drop points on each one of these different number lines. Now, just like we had before, we called this number line Rx, and we called this one Ry. That means this last number line needs a name too, and we're going to call it Rz. And then, to join this third point to the original two is no harder than it was before. You just go ahead and join these straight up. Now, for the particular points I've actually chosen, I want you to notice that the x-coordinate is 6, the y-coordinate is 4, and then the z-coordinate is 10, 9, 8. So we have 6, 4, 8. And that means that the coordinate I've actually drawn here is the coordinate 6, 4, 8. Now, because this 6 belongs to the x-axis, we will call 6 the x-ordinate. Because 4 belongs to the y-axis, it's going to be the y-ordinate. And then similarly, because 8 belongs to the z-axis, we'll call it the z-ordinate. And then, instead of calling this point 6, 4, 8, this 6 is x, this 4 is y, and this 8 is z. So this would be the coordinate x, y, z. So therefore, when we move to three-dimensional problems, all we really need to do is to just add one more axis, and therefore one more point. This will turn a 2D problem into a three-dimensional problem. But then, if moving to 3D is really easy with this kind of setup, then how would we do it for the other setup, for the Cartesian plane? Well, we can still move these two axes into place just the same way we did before. Now, by adding on an x-axis and a y-axis, you've technically used up the whole page. By moving left and right, you move along the x-axis, and by moving up and down, you move along the y-axis. So therefore, to add on the z-axis, you actually have to move out of the page or into the page. That's really all you can do. You have to do this in 3D, and that's impossible for me to properly draw on this two-dimensional screen. However, it's not very hard for me to draw three-dimensional things, so what I'm going to do is, I'm actually going to move this z-axis so that it points out of the page here, and you just have to imagine that we're looking at something three-dimensional. Now, just as we did in the previous example, let me go ahead and actually draw on a point for you, and then we'll see how it's similar, but also different to the previous example. Now, the way this point is currently drawn makes it very difficult to tell exactly where it is in three-dimensional space. But one thing I can do to help you visualize it is I'll go ahead and draw on the floor, and I want you to imagine some light actually shining down from the roof. So the shadow of this point ends up over here on the plane. So that means you can see that the point is a fair bit above the plane. Now, instead of actually projecting the point directly onto the x-axis and the z-axis, instead I'm going to project the shadow of the point onto the x-axis and the z-axis. Now from this, you can see that this is x equals 5, so the x-coordinate is just going to be x equals 8. And the z-coordinate, well, this is 5, so that means this is actually going to be z equals 4. Now the only thing left to find is the y-coordinate, and the way we're going to do that is we're going to draw a line diagonally from here to here, and then we're going to move the line up so that it lines up from there to there. And therefore, the y-coordinate is just going to be y equals 6 because it's 1 bigger than 5. So reading in the correct order, which is x, y, z, we have the point 8, 6, 4. Now just as we did before, we can replace every 8 for an x, every 6 for a y, and every 4 for a z. So instead of just adding on one extra axis, as we did in this picture over here, what we have to do is we have to add another axis that comes out of the page. So you don't just add the axis, but it also has to come out of the page. But then, thinking like a true mathematician, we then just ask the question, why not continue? Well, to move to 4D, this picture doesn't get any harder. You just add another axis, just as we did before. If you want to go to 5D, that's alright, just add one more axis. 6D, no problem. But for this picture over here, something pretty bad happens, to say the least. We live in a three-dimensional world, so therefore we only have 3 directions to play with. That's what three-dimensional means. There are only 3 primary directions. So if you did try to go x, then y, then z, where are you going to put the other axis? There are no other directions that you could use. We live in a 3D world. So to summarize this picture over here generalizes to 4 and 5 dimensions very easily. But this picture on the right does not generalize nicely at all. In fact, generalizing it, I'm going to call the mother of all headaches. If you want to really see what a 4-dimensional shape looks like, and you don't mind a bit of a headache, feel free to just look up 4-dimensional shapes. But I'm warning you, it is going to give you a headache. But at this point, I'd just like to summarize the lesson. In this lesson, we first started by reviewing the 2-dimensional Cartesian plane, and then we talked about how we could generalize it into 3 dimensions by looking at these 2 generalizations. For the first generalization, we just started with the standard 2-dimensional axis, and then we just added one more axis. Then we just picked an x, y, and a z coordinate and joined them with a string. This was completely analogous to what we did in 2 dimensions. In 2 dimensions, we just ignored z, and then we joined 2 axes with a string. We explained that it was really easy to generalize this method to higher dimensions, just by adding more and more number lines and making the string as long as we like. But then after this, we also tried to generalize the other way of looking at the Cartesian plane. We explained that to form the 3-dimensional Cartesian plane, you start in the exact same way. You just begin by starting off with 2 number lines that are 90-degree angles to each other. But then you use the 3rd dimension to actually add on the next number line. This time, if we choose a point, it needs to be done in 3-dimensional space. So to find its coordinate, we start by shining light down from the top and actually seeing where the shadow hits the floor. If we then look at the shadow, we can actually look at where it lines up with the x-axis to find its x-coordinate, and where it lines up with the z-axis to find its z-coordinate. And then after this, we can just look at eye level to figure out what the y-coordinate is as well. I might also mention that it is also possible to have another wall on the side of the room, and you can imagine shining a light to the left and seeing where the shadow lines up on the wall. As you can see from these 2 markings over here, the shadow looks like it's going to line up right here. So on the wall, you'd expect this point, and you could use it to find the y and z coordinate as well. However, the main problem with this method over here is that we found that it does not easily generalize to 4, 5, or 6 dimensions. If you tried drawing a 4-dimensional picture, your brain would just really not like it. It's very, very difficult to draw in 4D, and basically nobody can think in 4D. But I guess that's just because all of us are simple 3-dimensional beings, so thinking in 4D is just not something we've evolved to do. So as a result, despite the fact that you're going to spend most of your time looking at this form of the Cartesian plane, This method over here is actually much more useful as you move on to higher dimensions. Now, I might just quickly mention that there are ways that you can visualize four-dimensional objects by projecting them down into 3 dimensions or even 2 dimensions. It's sort of like looking at a 3D world through a photograph, where you project 3D down to 2D. I won't talk about that too much in this video, but maybe later down the track I'll make a video on that to explain it. So I think that just about completes everything I wanted to say about the 3D Cartesian plane. Now, it may be a while before you actually use it to start solving problems, but when you do start using it, you'll see that it's one of the most powerful tools that humans have ever invented to solve problems. And I'm sure you'll see that later on. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.